Okay, so sometimes in a greedy algorithm, to design the greedy algorithm correctly, we need to think about what the question is. And sometimes we need to rephrase the original problem's question a little bit. So here's an example that might give a little insight into how we can rephrase the shortest paths problem into something that's going to be easier to deal with. So suppose I give you a graph, just some random graph, who knows. And then I say, tell me all the shortest paths from, say, this, let's call that node up there in the top, let's call that the source. And I say, tell me all the shortest paths from that node to some other ones. And you go do something, right? You go do something, and you come back and you say, all right, here's the shortest paths. And then you start drawing them out. So the first shortest path you draw me, let's say is that one. Okay. So, it's clear that if you draw that shortest path and you say that's the shortest path from this node down in the bottom left up to A, it's clear that shortest path contains another shortest path, right? It contains the shortest path from this node to A. So that's nice. That's handy to know. And then you say, all right, now I'm going to focus on this node. The shortest path from this node, and I'm going to change colors here just to be, just to be fun. So from this node, the shortest path goes like this. Okay. So now what does this tell me? Well, it tells me that the shortest path from this node, goes through those two other intermediate nodes, which now for free gives me the shortest paths from those nodes. And then you say, hey, now I'm going to tell you the shortest path from here. So the shortest path from here goes up like this. And then, because now I already have the shortest path from this node, it follows along like here. Okay? And there, we're done, right? So those are the shortest paths. You come to me and you claim those nodes, those paths that I've just drawn are the shortest paths from all of the different nodes to that root node A. And then I say, hey, that's neat. You just drew a tree. And you said, well, I guess so. And as we look at it closer, and we think about what it means for the shortest paths problem to have optimal substructure, we'll eventually see that any way of writing shortest paths in one of these graphs defines a tree. Okay? In particular, it defines what's called a spanning tree. Okay, so let's make this observation. If I ask Dijkstra's algorithm, what are the shortest paths? From the source node to all the other nodes? The way Dijkstra will answer the question is it will give me a spanning tree. Okay, so Dijkstra always outputs a spanning tree. Always outputs a spanning tree. Okay, so real quick, it's worth mentioning what is a spanning tree. Well, a spanning tree is just a tree, right, which is an acyclic graph that contains only edges from my original graph, and it contains every node, right, and every node is connected. Okay, so we can define a spanning tree, and I should say, by the way, a spanning tree of the original graph, of the input graph. Okay, so just briefly, what's a spanning tree? So given a graph G, which is it's a collection of nodes and edges, V and E, a spanning tree is defined like this. A spanning tree of G, which I will call G prime, just to give it give it a name. So G prime equals V prime E prime, is a subgraph of G, and then so the thing that makes it a subgraph is the following. V prime equals V, right? So it contains exactly the same nodes. And E prime is a subset of E, right? So the subgraph cannot contain any new edges that don't exist in the original graph. And then the thing that makes this a spanning tree and not just a subgraph is that it's a tree that is connected to all the different nodes. So it's a subgraph of G that is first acyclic. Okay, and acyclic means that there are no cycles, right? There's no way to follow a path that leads you back to where it started. So it's acyclic and connected. So, and connected. Right? What does connected mean? It means that between any pair of nodes, I can get from one node to the other node, right? That there is a path connecting every pair of nodes, right? So no path comes back to itself. This is a little bit informal, but to itself. That's what acyclic means, and connected means that there exists a path between every pair of nodes. Okay, and so what Dijkstra's algorithm is attempting to do is to find a spanning tree of the original graph in such a way that that spanning tree expresses all of the shortest paths from A to each node. And we know that a spanning tree expresses paths, right, because of this, right? It gives us a non-trivial path, or it gives us a meaningful path from every node to every other node, and so that tells us it gives us a path from the root node to every other node. And the fact that it's acyclic means that those paths are unique. So if you say, what's the shortest path from A to D, and you have the spanning tree that Dijkstra's algorithm has given you, the fact that that spanning tree is a tree and is thus acyclic means that there is only one possible answer from that tree. It gives you exactly one possible path from A to whatever node you're looking for. Okay, so this is the idea of Dijkstra's algorithm, is rather than thinking about like coming up with a list of paths, let's think about coming up with a tree. Let's think about building up a tree step by step that contains shortest paths. And so our goal in Dijkstra's algorithm, thinking about this as a greedy algorithm, will be to build up a sequence of trees where at each step in the algorithm we add one more node to the tree, and that new node adds, it augments the number of paths, and so that in each step we're going to kind of be adding a new path to our list of paths. So at each step, each algorithm step, what we'll do is we'll add one more node to a spanning tree in such a way that that new node expresses a new shortest path. And the question is, how do you decide which node to add to the spanning tree at each step? Add a new node to tree that adds a new shortest path.